The subject of this lecture is how rocks can change form and composition, even from one rock type into another, without ever melting. This is the process of metamorphism, of which there are many types that involve environmental changes like increased pressure and temperature, hydrothermal activity, etc. These changes can occur for a number of reasons, like plate tectonic collisions, intrusions of magma, hot spring activity, even the occasional asteroid or comet impact. Let's review how the different types of metamorphism work. This image is of the Paleoproterozoic Trinity gneiss, exposed deep within the inner gorge of the Grand Canyon. This was originally an intrusive igneous rock, granodiorite, that formed around 1730 million years ago, and was later folded and metamorphosed into a gneiss during the Yavapai orogeny, which happened around 1700 million years ago. Metamorphism occurs as environmental changes occur to the original rock type, otherwise known as the protolith or parent rock. Metamorphism involving increasing pressure, temperature, and/or fluid activity causes the protolith to progressively change in form over time. All this occurs without melting the rock. New metamorphic minerals may grow, depending on the metamorphic conditions and the composition of the protolith. For example, as a mudstone protolith experiences progressively higher pressures and temperatures, mineral crystals may grow larger and the platy minerals will become more well aligned. New minerals like muscovite, biotite, and garnet may form. Thus, a mudstone sedimentary protolith can be transformed into a totally different metamorphic rock, like this garnet-bearing schist. Once again, we return to the diagram of the rock cycle and how metamorphism fits into the rock-forming process. Metamorphic rocks can be formed in a number of ways. For instance, a pre-existing intrusive igneous rock like granite may be squeezed and heated by tectonic processes to form a metamorphic rock, a gneiss. An extrusive igneous rock like rhyolite at the surface of the Earth may be buried or subducted and also changed into a metamorphic rock, a metarhyolite. Sedimentary rocks can also be changed by increasing temperature, pressure, and fluid activity. One example is a sandstone being heated by a nearby intrusion to form quartzite, or a mudstone being squeezed and heated to become slate. Even metamorphic rocks can experience metamorphism more than once. All of these changes occur without melting of the rock. This diagram relates to metamorphism that occurs at depth, well below the Earth's surface. Not portrayed in this diagram are metamorphic processes that occur along fault zones or shear zones, or at asteroid or comet impact sites. In general, metamorphic grade describes the intensity of metamorphism, specifically the intensity of increased temperature, pressure, and fluid activity that occurs during metamorphism. This diagram is called a PT diagram, and let's look at it a little more closely. This shows the different pressure and temperature conditions within the Earth. Temperature in degrees C increases from left to right, and pressure is in kilobars, increases from top to bottom. There is a relationship between pressure and depth, as the pressure increases with depth at around 1 kilobar for every 3.3 kilometers of depth. Low metamorphic grades describe the relatively low temperatures and pressures found at more shallow depths, whereas high metamorphic grades describe the higher temperatures and pressures typically found at deeper depths. The diagram at right shows the sequence of minerals that progressively form under different metamorphic conditions. Zeolites, chlorite, sodium-rich plagioclase typically form at lower metamorphic grades, whereas garnet, pyroxene, and calcium-rich plagioclase form at higher metamorphic grades. Some minerals form under certain metamorphic conditions. These index minerals record the metamorphic conditions or metamorphic grade that existed when the mineral was formed. Formation of each index mineral depends on specific pressures and temperatures as well as the composition of the protolith. Shown here is a mudstone sedimentary protolith and the metamorphic rock schist, which includes large crystals of garnet. So this metamorphic rock may actually be called a garnet schist, garnet-bearing schist, or even a garnetiferous schist. The table at right shows the sequence of minerals formed from different protoliths. A shale or mudstone sedimentary protolith can produce a sequence of metamorphic minerals ranging from muscovite and chlorite at lower metamorphic grades to biotite, garnet, and pyroxene at higher metamorphic grades. The fact that our sample contains garnet indicates that it experienced moderate to high-grade metamorphism. Garnet commonly forms from mudstone protoliths because mudstone contains abundant aluminum necessary to grow aluminous minerals like garnet. Other protoliths have different compositions, and so different minerals may form during metamorphism. Minerals like epidote, chlorite, and amphibole typically form from a basaltic protolith, as well as garnet and pyroxene at higher metamorphic grades. First, let's talk about pressure. There are two basic types of pressure encountered during metamorphism: confining and directed. Confining pressure is where the rock experiences equal amounts of stress from all directions. Confining pressure is also known as lithostatic pressure within the solid earth. Lithostatic means rock equal, basically. Confining pressure is also known as hydrostatic pressure within watery environments like the ocean, hydrostatic or water equal pressure. In either case, because the stresses are applied uniformly, the resulting arrangement of crystals or grains in a rock stays the same. This non-foliated metamorphic rock texture is not layered and lacks any new preferred orientation of minerals. So, equal stresses applied from all directions yield a non-foliated rock texture with no preferred orientation of minerals. Directed pressure is where rock experiences different directions and/or amounts of tectonic stress. The resulting arrangement of crystals or grains in a rock changes as the platy minerals become more aligned relative to the stress directions. This takes place very slowly and in the solid state, with no melting of the rock. This diagram here shows how randomly oriented platy minerals can reorient themselves under different types of directed stresses, whether it's compression or shear. An alignment takes place over time as those minerals start to reorient in a similar fashion. An analogy would be, instead of a cube of rock with platy minerals, maybe it's a cube of clay, and let's say you have a bunch of pennies and you're sticking them in there randomly, and then you start to apply pressure, say you're squeezing that cube. Those pennies are going to realign very slowly so that they're more or less layered perpendicular to the incoming stress. And that's what we see here in this example. If you sheared that cube of clay, a similar texture would start to develop that we see here in this example. This middle diagram shows how a foliated metamorphic rock texture can form. The rock there on the left is a typical granite with platy minerals like biotite, and over time, if it's subjected to tectonic compression, those biotite grains may realign so that they're more stable under the new stress conditions. And so they become aligned in a roughly parallel fashion, and that layering is about at right angles, about perpendicular to the incoming stress. This develops very slowly with no melting occurring in the rock, and the new rock texture is called foliated. In that layered texture there, you can see that metamorphic rock type gneiss. So the resulting foliated metamorphic rock texture is layered due to the preferred orientation of these platy minerals. This is an image taken through a polarizing microscope. So you're looking at a thin section of rock, only about 30 microns thick or so light passes through it, and it's filtered with a couple filters that the light passes through, and that's why the different minerals are different colors. And so you can see here that the minerals have a preferred orientation because they've been subjected to some kind of stress. It could have been shear or tectonic compression. The bright pink minerals are biotite, and the gray ones are quartz. So you can see how the quartz doesn't really have a layering to it, but the bright pink biotite does. That's foliation on the microscopic scale. So the resulting foliated metamorphic rock texture is layered due to the preferred orientation of these platy minerals. Notice the asterisk there, and that's because protolith lacking significant amounts of platy minerals will not likely form a well-developed foliated texture, even if it's subjected to tectonic compression or shear stresses. There's simply not enough minerals to form that layering. You can think about that cube of clay again, and if you stick it full of pennies and squeeze it, those pennies will become realigned and you'll get some kind of layering. If you take the cube of clay and there's no pennies, and then you squeeze it, you won't get much layering in the clay. And so it's a similar situation in rocks. Heat is another major factor that drives metamorphism. The most common sources of heat include sedimentary burial, tectonic plate subduction, and nearby igneous intrusion activity. Progressive burial of sediment, deeper and deeper over time, leads to an increase in temperature. The amount of increase depends on the geothermal gradient of the area. A volcanically active region will have a higher geothermal gradient than, say, a stable mid-continent area. Another source of heat is tectonic subduction, which actively drags oceanic lithosphere deeper and deeper into the Earth's mantle. This leads to an increase in the temperature of the downgoing plate, gradually heating up the plate from the outside. Another effect of this subduction-related heating is the release of water and other fluids, we call volatiles, from the subducting plate into the overlying mantle. So in this diagram here, these dashed lines are different temperature isotherms. Okay, the 300 degrees C isotherm, 600 degrees C. And so as the plate goes down, it's basically coldest in the middle and it starts to heat up from the outside in. And the deeper it goes into the mantle, down in the subduction zone, the warmer it gets. And so that 300 degree C isotherm disappears and it's replaced more or less by higher temperatures. And as this happens, the mineral crystals start to change and water gets flushed out of that plate into the overlying mantle, whether it's the asthenosphere or the lithospheric mantle. And again, the addition of water into those hot rocks lowers their melting temperatures and you can form magmas. A third source of heat is from intrusive activity. Depending on the size of the intrusion, heat will radiate some distance into the surrounding wall rock or country rock. Magmatic fluids also help to transfer some of this heat into the nearby rock. The migration of heat and fluids into the surrounding rock may alter the rock and produce new minerals in a zone surrounding the pluton called a contact aureole, or simply bake zone. Relative to smaller intrusions like dikes and sills, the metamorphic effects of larger plutonic complexes are more pronounced and widespread because these bodies possess more heat and stay molten for longer periods of time. So in this example here, we have the magma, the country rock, which is sedimentary rock limestone, and then the bake zone around the magma body is the contact aureole, and that's where we form metamorphic rocks. Discussion of the effects of fluid activity in metamorphism are often overshadowed by those of pressure and heat. Nonetheless, hydrothermal fluids, or hot water essentially, are extremely important in many metamorphic environments. This hydrous fluid activity helps drive chemical reactions that alter the surrounding wall rock and create new minerals. Heat is also transferred by the fluids, and dissolved material can be transported as well. Hydrothermal fluids can originate in several ways. One is by confining pressure of progressive sedimentary burial, forcing fluids from the pore spaces between the grains and creating hydrothermal fluid activity, depending on the geothermal gradient. Another way that hydrothermal fluids originate is from the cooling and crystallization of magmas, driven under pressure out of the magma into fissures in the surrounding wall rock, and in turn, surrounding groundwater may be heated by this magmatic heat and fluid activity. Finally, the increasing temperature encountered during subduction can cause minerals in the downgoing plate to change form and release water. These hydrothermal fluids then migrate upward into the overlying plate. Metamorphism occurs in all plate tectonic settings, and the resulting metamorphic rocks that are created can tell us about metamorphic environments or metamorphic facies that exist deep within the Earth. Geologists like Dr. Carl Karlstrom study metamorphic rocks and minerals in hand sample and in thin section to get a basic handle on the type of metamorphism and where and how it occurred. For example, some metamorphic rocks like gneiss typically form at deeper crustal levels than rocks like slate. Study of thin sections under the microscope is usually necessary to yield more details about the metamorphic environments in which these rocks may have formed. A simple DT diagram, or PT diagram, since we know that pressure correlates with depth, shows the basic metamorphic environments within the Earth, and these environments are also called metamorphic facies, with each facies representing an area of certain pressures and temperatures within the Earth. And there's different varieties: low temperature, low pressure ones, high temperature and low pressure, call that contact metamorphism. There's low temperature and high pressure, call that blue schist facies. And there's others: green schist, amphibolite, granulite, eclogite, all depending on the pressures and temperatures of metamorphism. As we said before, metamorphism occurs in all plate tectonic environments, and the ultimate goal is to study metamorphic rocks and structures so we can relate them to real-world plate tectonic environments. So now let's review the main types of metamorphism and where they occur. Depth temperature diagrams like this are commonly used to show the different types of metamorphic facies. The low pressure, low temperature facies is called diagenesis. This is essentially sedimentary burial. The low pressure, high temperature facies is called contact metamorphism. There's a broad metamorphic facies called regional metamorphism, which encompasses variable pressures and temperatures from lower metamorphic grades to higher metamorphic grades. Hydrothermal metamorphism includes water and high temperatures. Shock metamorphism is ultra-high pressures and temperatures from asteroid and comet impacts. And dynamic metamorphism involves high pressures and variable temperatures that exist along fault zones and shear zones. Hydrothermal, shock, and dynamic metamorphism are not portrayed in this diagram. Diagenesis, also known as protometamorphism, burial metamorphism, or even lithification, involves low pressures and temperatures that typically occur during progressive sedimentary burial. In essence, this is lithification, where sediment is transformed into sedimentary rock through compaction and cementation. Contact metamorphism involves high temperatures and relatively low pressures from intrusive activity that produces changes around the margin of an intrusion, whether it's a large batholith or a small dike or sill. The zone of contact metamorphism around an intrusion is called a contact aureole, or simply bake zone, and its width is proportional to the size of the intrusion. Larger intrusions release more heat and fluids over longer periods of time than do smaller intrusions, thus affecting greater areas of wall rock. So, the bigger the intrusion, the wider the contact aureole. The larger batholithic complexes may have very wide contact aureoles, tens to hundreds of meters or more wide, whereas thin dikes and sills may have little, if any, meters to centimeters or less. Hydrothermal fluid activity is an important aspect of contact metamorphism and typically helps transform the composition of the surrounding wall rock. Depending on the composition of the wall rock and proximity to the intrusion, distinctive index minerals may form, like sillimanite, staurolite, kyanite, that commonly form in these contact aureoles. The relatively high temperatures and low pressures transform the surrounding rocks in place, and the resulting rock textures are termed non-foliated due to the lack of significant layering. Common transformations include sandstone into quartzite, limestone or dolostone into marble, basalt into metabasalt or greenstone, etc. Hydrothermal metamorphism is similar to contact metamorphism, but involves more fluid activity. You can consider it essentially a wet contact metamorphism. Hydrothermal fluids are typically composed of water with significant amounts of dissolved mineral content. Hydrothermal systems are related to intrusive activity and originate from cooling and crystallizing magma bodies. The fluids move through the rock and along fractures, commonly interacting with and heating up the surrounding rock and groundwater or seawater. Hot springs, geysers, submarine black smokers are all driven by hydrothermal fluid activity. Regional metamorphism involves variably low to high temperatures and pressures related to tectonic activity, typically applied over areas of hundreds to thousands of square kilometers, hence the name regional. As temperature increases with depth, the effects of regional metamorphism become more pronounced with depth. Elevated pressures and temperatures are common at active tectonic margins. This includes continent-continent mountain building areas and ocean-continent and ocean-ocean subduction zone areas. The directed pressures and temperatures of regional metamorphism transforms rocks in place, and the resulting rock textures are termed foliated due to the pronounced mineral layering. Foliation evolves into different forms as pressure increases during metamorphism. Common transformations include mudstone into slate, phyllite, schist, and/or gneiss, basalt into green schist, granite into gneiss. It should be noted, again, that a non-foliated texture may result if the protolith lacks enough platy minerals to form foliation. Quartzite and marble are examples of non-foliated metamorphic rocks that can form from regional metamorphism. As with contact metamorphism, hydrothermal fluid activity helps drive the chemical reactions that alter pre-existing rock and create new minerals, like amphibole, pyroxene, garnet, sillimanite, kyanite, staurolite, you name it. Dynamic metamorphism involves localized high pressure changes along fault zones and shear zones. Brittle deformation in the form of crushing and brecciation occurs from high pressures along upper crustal fault zones. This is also called cataclastic metamorphism. Shown here are altered and crushed rocks along a low-angle fault zone in western Arizona. Deeper in the crust, where the temperatures are higher, ductile deformation occurs along shear zones and produces layered myelinites and elongated taffy-like structures. Shock metamorphism involves the localized ultra-high pressures that occur during an asteroid or a comet impact, which produces various results in the surrounding rock. The extremely high temperatures at the impact site create impact-related melt, which cools to become glass. Away from ground zero, the shock wave shatters rocks into fragments, including impact breccia and smaller material. Shocked quartz occurs where the crystal structure of individual mineral grains is deformed by the shock wave. Much of this material is thrown out of the newly formed crater and forms an ejecta blanket around the impact site. Well, that's all for now. Till next time.